All right, so very quickly we got this. All I did is take the example that we have and assign some values here. Let's make I 24 milliamps like that. Okay, let's think it through first of all. You understand the problem. What we're after is pretty much everything. So I sub C, I sub L, I sub R, and V. So we want to know all of those quantities right there. Now there is a discontinuity at t equals 0. Switch is open, current begins to flow, and initially all of the current at t equals 0 plus, all the current in form of displacement current is going to go through the capacitor. That's because right at t equals 0 plus, there is no resistance here. Now that's slowly going to build up a resistance, so we'll have currents being shared here. So, but the point is, right at t equals 0, there is no current going through anything except the capacitor there. All right, what about much later on? Much later on, all of the current's going to be going through the inductor, and that's because the inductor is going to behave like a wire. So I sub L at 0 plus, now this is right at t equals 0, is going to be 0. And why is that? Well, that's because I sub L at 0 minus was 0, and you cannot have an instantaneous change in current for an inductor like that. So that has to be 0. All right. Then what about the voltage at 0? Well, the voltage at 0 is also going to be 0. For the same general reason, you cannot have an instantaneous change in voltage for the capacitor, and everything here has the same voltage. So if that is the case for the capacitor, that will be the case across the board here. Okay, what about final values? Well, V at infinity, a long time later, that's what we call V final. So that's also going to be 0. And again, the reason it's going to be 0 is because after a long time, all of the current's going through the inductor, and it behaves like a wire, and the potential across a piece of wire is just 0. All right, then that's, let's say, I sub L at infinity. What's that going to be? Well, at infinity, that's just going to be this big I. So that's going to be 24 milliamps after a long time. Okay, now we've got these initial conditions here. Usually we can find one of the coefficients for our natural case using these, but the second coefficient we have to have the derivative. So we've got the relationship between voltage and currents that we can use now. So di sub L dt, you know that that's going to be V at 0 plus divided by L. This is evaluated at 0. And you know that that one right there is 0. So this whole thing is going to be equal to 0. Now that may not be the case here with dV. dt is going to be I sub C over C. So evaluating that at 0. What is I sub C at 0? Well, I sub C at 0 plus is going to be all of it. So this is going to be 24 milliamps divided by C. So you could do that computation to figure out what that's an actual number there. Okay, so those relationships here and here are going to help us figure out what our coefficients are for our voltages and currents. We'll go through most of this. I'll skip some steps to show what the numbers are, but alpha is going to be 1 over 2 RC. So that's going to be 1 over 2 times 400 times 25 times 10 to the negative 9th. And that turns out to be 5 times 10 to the 4th, which makes alpha squared 25 times 10 to the 8th. All right, so we've got our alpha squared. What about our omega naught squared? That's 1 over LC, so that's 1 over L, which is 25 times 10 to the negative 3 times C, 25 times 10 to the negative 9th. And omega naught squared turns out to be 16 times 10 to the 8th. Okay, so you can see the relationship here between alpha squared and omega naught squared. Alpha squared is larger. So what this means is that S1 and S2 are going to be distinct real numbers because what's underneath the radical is positive. Okay, so we're ready to do S1 and S2, but let's see, so which case is this? This is the overdamped case. And S1 is going to be minus alpha plus the square root alpha squared minus omega naught squared. That number is going to turn out to be minus 20,000. And S2 is going to be minus alpha minus the square root alpha squared minus omega naught squared. And that turns out to be minus 80,000 there. All right, since we know it's the overdamped, we know the general solution is what that's going to look like. So we can go ahead and write that down. So it just depends on what you want to go for first. Let's go for I sub L. So I sub L is going to be I final plus the natural response. The natural response for overdamped is going to look like this. A1 prime e to the S1 t plus A2 prime e to the S2 t. I just put primes on the coefficients to indicate that they're different than what they might be for the voltage. All right, so we know what I final is going to be. That's the 24 milliamps up here. And we are ready to evaluate our coefficients here. Well, I sub L at 0 plus is going to be I final plus, and now we evaluate this at t equals 0. So it's going to be A1 prime plus A2 prime. And we know that that is equal to, based upon our analysis up here at the top, 0. Okay, so there is one equation, one of the two equations that we'll use to evaluate our coefficients. The other one is going to involve the derivative, which is this right here. So we know that the derivative of I sub L with respect to t evaluated at 0 plus is also 0. You take the derivative of this with respect to time. The I sub f, because it's a constant, goes away, and we're left with A1 prime S1. Again, evaluated at t equals 0, the exponentials go to 1, plus A2 prime S2. There is our second equation there. Okay, so we've got our two equations, two unknowns. You should be able to go through the process of solving those two right there. I am just going to jump to the solution here. A1 prime is negative 32 milliamps and A2 prime is 8 milliamps. Okay, so now we can jump to the final solution for our I sub L. I sub L as a function of time. I left off the function of time there, but you understand that that is going to be time varying. Equals, now I sub F, 24 milliamps plus A1, and that's going to be negative, so I probably should have made that a negative there. Pretend that that is a negative. 32e to the negative S1, 20,000 t plus 8e to the negative 80,000 t, and the units here are milliamps. Okay, so we've got our I sub L at this point. Now, I sub L, you can use that I sub L, and now you can compute voltage, let's say. V equals L di dt. That's the relationship between voltage and current for the inductors. So specifically, this is I sub L right there. Okay, so how would you do that? You'd go back over here, take the derivative of this with respect to time, multiply by L, and you would end up with this value. I'm going to go ahead and tell you what the answer is for that. You might want to work it out yourself. E to the negative 20,000 T minus E to the negative 80,000 T, and that's volts. Now, if you go through and you work this out, you discover that the coefficients for the voltage happen to be exactly the same. So at T equals 0, this becomes 0. All right. Now, let's say, for example, that you were given this problem exactly the way it looks here, except you were asked to find only the voltage. Find the voltage. Well, to find the voltage, you wouldn't want to go through this process of finding I sub L first, then doing the derivative like this. If you were asked to do it that way and find only the voltage, you should take the other approach that says the voltage is equal to V final plus the natural response. And the natural response is going to be A1 e to the S1t plus A2 e to the S2t. Now S1 and S2 are going to be exactly the same as they were up here. Your A's are going to be computed using the same technique, but they are going to be different than this A1 prime and the A2 prime, because the A1 prime and the A2 prime apply to the current for the inductor. So if you start with something like this, well, you just go through the process. S1, do the calculation, is going to be exactly the same, minus 20,000. S2 is going to be minus 80,000. You would do the comparison between alpha squared and omega naught squared to show that this is going to be the form of the solution. And then, well, you would go about solving for these coefficients A1 and A2. The V final, let's see. V final, according to our analysis, is going to be 0 here. That's V at infinity. So V final is 0. All right, so we know that that term right there goes to 0. So we're just left solving for A1 and A2. Well, you use your initial conditions. V at 0 plus is going to be 0, so you take your voltage function here and you evaluate it at T equals 0. The exponentials will go to 1, and we're left with A1 plus A2, like that. Okay, then the other, there's one equation right there that we'll use to solve for our coefficients, but we have two coefficients, so we need a second equation, and that one involves the derivative. dV dt evaluated at 0 plus is going to be I sub L evaluated at 0 plus divided by L. Okay, geez, that's a mistake. I sub C divided by C. Okay, now I think we've got that. So I sub C at 0 plus, let's see, what was that one? That's the 24 milliamps divided by C. So that's going to be 0.024 divided by our C value, and let's see, what was our C value? 25 nano. So this is going to be 25 times 10 to the negative 9. All right, and that is equal to the derivative. So take the derivative of this up here, evaluate it at T equals 0, and you end up with A1 S1 plus A2 S2. So here is our second equation. This one was our first. So now we've got two equations, two unknowns. S1 and S2 are these values up here. So you should be able to solve for that. And I showed you this because I wanted you to see that you could have gone straight for the voltage. You could, instead of going through finding I sub L first, like we did here. But if you do happen to find I sub L first, then you can use this technique to get your answer. I'm not going to go through the steps again. I want you to be able to do that, but you do turn out, if you solve for A1 and A2, you do get that same answer right there. Okay, now from this you could find I sub R. I sub R is just going to be V over R, and that's true for all times. So if this is our expression for V, then we just plug that in, 16 e to the negative 20,000, t minus e to the negative 80,000, t over R, which was 400 ohms. Okay, and you can simplify that down, and I believe you get 40 times e to the negative 20,000 t minus e to the negative 80,000 t, and that is in units of milliamps. Okay, then what about I sub c? Well, I sub c is c dv dt, so you could find it that way. Take c and take the derivative of what goes in the parenthesis here is the voltage function. Okay, that's one way to do it. Another way to do it would be to say, well, I sub c is going to be of the form I sub c final plus the natural response, A1 e to the S1t plus A2 e to the S2t, and that would be the other way that you could go through there. This A1 and A2 are different than the A1 and A2 up here, so you might want to call that something else like double prime. Okay, the S1 and S2 would be exactly the same. So very similar to what we did here, you could do the same process here. Use your initial conditions for I sub c, for I final, to figure out what what these coefficients are going to be. Another way to find I sub c would be to realize that I sub c is going to be big I minus I sub r minus I sub L. So that just says that the sum of the currents leaving that top node is equal to big I. And you can see that here. If this is the top essential node up here, then those are the currents leaving, and this is the current going in. So the sum of the currents leaving is equal to the sum of the, that's just KCL. Okay, so there's about, once I've got I sub R and I sub L, then finding I sub C by this way is another possibility. Okay, so any of these components, whether it is V or whether it is I, and that I could be I sub R, I sub L, I sub C, any of those, we know that it's going to, the general solution is going to look like V final plus the natural response. Or I final plus the natural response. So probably the hardest part of this is figuring out the coefficients and figuring out what these final values are. But after you do that, it shouldn't be too hard. So how do you approach a problem like this? Well, the same general approach applies. Understand your initial conditions, determine which of these responses you're interested in, and solve for whichever one you're asked to solve for, or just pick one first and solve for it. After you have that, then usually the others will fall out from there. So you can solve for V, you can solve for I sub R, I sub C, I sub L, all of those out of this. Then once you've got V and I, you could potentially go on and solve for power. You could potentially go on and solve for energy as well. But that's enough for this problem. Okay, we're going to solve this problem right here. This is parallel RLC. We've got this R, L, and C values, and we've got some initial, we've got this source current over here. At t equals 0 is when that switch is thrown, and that's when currents begin to flow through all of the elements here. That's I sub R, this is I sub L, this is I sub C, like that. Okay, let's do our computations and work our way through this. Alpha is going to be 1 over 2RC, so that's going to be 1 over 2 times 625 times C is 25 times 10 to the minus 9th. I'll do that calculation. That turns out to be 32,000. Okay, so alpha squared is 10.24 times 10 to the 8th. And then omega naught squared, since we've worked this type of problem before, it depended upon L and C. We've only changed the R from the previous problem here. So this is going to be 1 over LC. That's going to be 1 over 25 times 10 to the negative 3 times 25 times 10 to the negative 9. And that is 16 times 10 to the 8th. So we've got a situation here where alpha squared, omega naught squared, you can see which one is bigger here. The omega naught squared is larger. So this means that what's underneath the radical for S1 and S2 is going to be a complex number. So what does that mean? That means that everything is going to have this general form, that I is going to be I final plus the natural response, and the natural response is going to be B1 prime e to the negative alpha t times the cosine of omega sub d t plus B2 prime e to the negative alpha t times the sine of omega sub d t. Voltage also is going to be of this form, V final plus B1 e to the negative alpha t cosine omega sub d t plus B2 e to the negative alpha t times the sine of omega sub dt. These coefficients are going to be different for each one of those. The alphas are all the same, the omega sub d's are all the same, and these final values are likely to be different for each one of those. Now, I'm not going to go through the process here. I want you to do that as an exercise, and I want you to find I sub r, I sub l, I sub c, and v for everything. Do that on your own. This is not an exercise where I'm going to take it up as a homework or anything like that. But you need to be able to do this. You will be asked, I guarantee you will be asked to do at least some of this when it comes time for your next exam. Guarantee it. So do this as an exercise on your own.